Thank you. Okay, so thank you. I'm going to tell you a few words about loop quantum cosmology, especially focusing on possible observational or experimental aspects. So, in the last years, I think that cosmology has focused on quite a lot of different issues with many successes: nucleosynthesis, neutrinos, origin of black holes, formation of structure, physics of baryons, dark matter, dark energy, and so on and so forth. But probably the most outstanding questions of all, that is the question of the origin itself, was still somehow outside the field of hard or mathematical science. And I think that the situation is changing right now for two different reasons. One is observational. I mean, of course, it happened to be wrong. But for a few weeks or months, you remember that most of us thought that the BICEP2 experiment had discovered primordial gravitational waves. And it will probably happen in the near future. But primordial gravitational waves that have imprints on the cosmological microwave background B modes must be of quantum gravitational origins, at least in most scenarios. So this is something very interesting because it means that probably in the next decade, quantum gravity will really enter the sphere of observational science. This is not just a claim or a hope. I mean, it's something that is becoming real. And of course, on the other hand, on the theoretical side, we have seen a lot of recent progresses, and I am now going to focus on a specific proposal which is called the loop quantum cosmology. So for those of you who know nothing about loop gravity, I just take 3 minutes to remind you the basic settings. So in a nutshell, the hope of loop quantum gravity is to try to construct a quantum theory of space-time using only what we think we know about general relativity and quantum mechanics. Of course, this is a hard task, and this is why it took so long to achieve this, this level of understanding. So the bet of the theory is to trust diffeomorphism invariance. I mean, to consider that diffeomorphism invariance is really a fundamental theory of nature, which might be wrong. I mean, of course, it could be that, at high energy, this symmetry is broken. Of course, this symmetry has very fascinating mathematical properties, but I think we should underline that it also has a philosophical meaning. I mean, this is really the heart of the relativistic or relational view of the world. This is what leads us to a kind of Leibnizian vision of the world. So it's a bit more than mathematics, okay? Taking diffeomorphism invariance seriously is also a kind of metaphysical assumption that you make about what the world is. There is no background structure at all. So the idea is the following. You begin with a foliation of space-time, like in the ADM formalism. So you have space slices, you define the three metric, and then you have the conjugate momentum, which is a derivative with respect to the normal surfaces, and this is the extrinsic curvature. So you have a pair of variables, you want them to be solutions of the Einstein's equation, so you impose the diffeomorphism and Hamiltonian constraints that ensure the local symmetries and the evolution of the theory, and you can perform a quantization à la Dirac by promoting the Poisson brackets to be commutators. If you do that naively, you end up with the Wheeler-DeWitt theory, which is very well known, which is very nice actually, but whose main problem is that it has been unable to make any real concrete prediction. And one of the reasons for that is that it's very hard to define an inner product between metrics. And without inner product, you don't have a clearly defined Hilbert space, and this is what you want to make predictions to compute amplitudes in quantum mechanics. So this is the main reason why you switch to so-called HTK variables, so namely the spin connection and the densitized triodes that are known to have very interesting properties for quantization. But as in any field theory, you need at one point some smearing of the field to get rid of the delta functions, and this is why you actually use not really HTK variables, but the holonomy of the HTK connection and the flux of the densitized triodes. And that's the basic setting for loop quantum gravity. If you are a particle physicist, you can think about that as an equivalent of lattice quantum chromodynamics. What you do in lattice QCD is the following. You define a graph and a Hilbert space which is given by the space of squared integrable function over the quotient of j to the L to j to the n, where L is the number of links n is the number of nodes, and j is your gauge group. And you define the Fock space by taking the appropriate limit. This is basically what is done here. In this case, the gauge group is SU2 because the HTK connection is SU2 valued, and you factorize by the automorphism group to ensure diffeomorphism invariance. You have natural operators that you can define on this space, and the Penrose theorem together with local gauge invariance leads you to a very nice and I would say intuitive interpretation of this as a kind of discretization of space. But don't take it literally. I mean, you have to think as a superposition of discretization of space. I mean, this is highly quantum. And the so-called spin network basis is the one which diagonalizes the area and volume operators. The point is that this theory, the spin foam theory, which is also called the covariant theory, has now been shown to be equivalent to the canonical theory. So depending on what you want to do, you can use basically one or the other. Loop quantum cosmology is the application. Yes. I don't plan to, but maybe in the discussion we can discuss that. Yeah, I mean, there are a lot of studies about that, and there are a lot of hints that the continuum limit is well defined. I mean, it's very complicated. There are two limits. There is a continuum limit, and there is a classical limit, and you have to define them properly. But yes, there has been a lot of progress on that recently. Yes. Sorry. It depends how you define the continuum limit. There are many different ways of defining the continuum limit. So we could discuss a lot about that, but my point today is not to discuss the fundamentals of the theory, is to discuss the application of the theory to a specific system, which is the universe.
So can we skip this discussion to the end, please, so that we can continue with this talk?
No, I mean, it is clear. The point is that as is any speculative theory, there are different approaches. That's all. There are different possible solutions. There are different ways to understand it, as in all quantum gravity theory we might discuss today. I mean. So within the standard quantum geometrical dynamics, the problem is that the Big Bang singularity is not resolved. But I mean, I would like to emphasize from right now that I mean, I think it's unfair to say from the beginning you cannot play with this theory for such and such reason. I mean, we don't have a single quantum theory which is perfectly defined at that time, correct? I mean, if you have one, tell me which one, okay? So we have here something which is mathematically well defined, whose limits have been studied into many details, which converge toward Ray-J calculus, and Ray-J calculus is is known to be a discretization of JR. So, I mean, I think we have to be very careful about a priori arguments, okay? Because we can have very easy a priori arguments against absolutely any theory, right? So the key questions in cosmology that I want to address are the following. So I would like to show you that we can go quite close to the Big Bang with the notion of smooth space-time, and that inflation is a safe setting in this framework just because space-time is already completely continuous at that time. In a way, inflation is predicted by the model, and here I would like to explain into quite details what I mean by this. The Big Bang singularity is somehow solved in the same way that the hydrogen singularity is solved in standard quantum electrodynamics. You don't need any principle or boundary condition like the Hartle-Hawking condition proposal or something like that at the Big Bang. The evolution remains deterministic through singularity, so you can really compute through many possible cycles. And of course, if you don't have singularities, you have another side of the singularity, and you can see that obviously with this modified Friedman equation. So this is the standard Friedman equation. This is h squared, and this is a quadratic correction which comes from the theory with the correct sign. And you see obviously that because this term is positive, this rho, the density of the universe, has to be smaller than the critical density, which is of the order of the Planck density. So it is bounded from above. The states remain sharply peaked for a large number of cycles. arguments can be extracted from the wave function to serve as an emergent time, so you can intuitively still think with time. And of course, the important point to keep in mind is that the quantum geometrical effects are huge in the Planck era, where the classical forces are extremely attractive, and then the quantum effects integrated over 4 billion years are small enough so that the theory is completely equivalent, of course, to JR for contemporary predictions. So, of course, the important point is that the uniqueness van der Waals theorem is evaded in this context because the theory is an equivalent to the Wheeler-DeWitt theory already at the kinematical level. You don't have any more a difference equation, you really, a differential equation, you really have a difference equation. And the key point is the following. So this is, if you want, time, and this is size. This is a scalar field, and this is a volume. The red crosses, I'm sorry for low quality, the red crosses is a classical expanding solution of the universe. Okay, this is a singularity, this is a classical expanding solution, and this is a classical contracting solution. And the red dots are the outputs of LQC. So of course, today, the JR and LQC completely agree, and when you go backward in time, what happens is that instead of following the classical trajectory to the Big Bang, the universe bounces, and you link the classical contracting branch to the classical expanding branch by a kind of tunnel effect. And this is why, of course, in this setting, we don't speak anymore of the Big Bang, but of the Big Bounce, which means that around the Planck density, the universe bounces, so there is a contracting branch, a bounce, and an expanding branch. So the singularity resolution in LQC is now quite robust. It has been explicitly shown for exactly solvable models, flat, isotropic, and with a massless scalar field as a content. Then with both positive and negative spatial curvature, it has been shown for an isotropic Bianchi universe with both a negative and a positive cosmological constant, with a massive scalar field, and also with highly quantum states. So let me just explain at the intuitive levels what happens with a massive scalar field assumed to be the content of the universe. So this is the classical standard Klein-Gordon equation, and this is the so-called friction term. So although what I'm going to say now is not completely correct, this just gives you a flavor of what is happening. The flavor is the following. During the contraction phase, the Hubble parameter is negative, right? So this is not friction, this is anti-friction, and therefore the oscillations of the field are amplified. The field climbs up its potential, but just after the bounce, the Hubble parameter is big and positive, and therefore, because of the friction, the field is frozen at the top of its potential. This is exactly what you need and what you want for inflation to take place. So we have to be very careful here. It would be wrong to say that loop quantum cosmology predicts inflation as something miraculous. This is not the case, okay? Actually, it predicts as the energy scale. And of course, if you begin with a massive scalar field at the Planck scale, you nearly inevitably end up with inflation, because inflation is an attractor. This is well known, of course. So you don't need anything magical. I mean, if you take a massive scalar field at the Planck energy, you basically always have inflation, whatever the theory. So it's not difficult to have inflation. The problem is to have the correct energy scale, and this is basically what it does for you. So the important question is to set initial conditions for understanding the background dynamics. X is basically the square root of the fraction of potential energy density at the bounce, and this is time. This plot, for example, describes no deflation, the bounce, and inflation. Here you have deflation, which is the time reversal of inflation, right? Here you have deflation and no inflation. Little deflation, big inflation, etc. For well-chosen initial conditions, all those situations are possible. But the main point I want to make right now is that they are not equally probable. That's not time symmetrical, and that's the key point. What I mean is that this situation, no deflation and inflation, is highly probable. This situation is nearly impossible to reach. And the reason is the following. There is a phase which happens in the dynamics of the universe, which is obviously the random parameter you want to choose, because it is here that you want to take a flat probability distribution function, and for mathematical reasons you can show that this is the only distribution which is preserved over time, so it really makes sense. And if you... Sorry? You can, of course. If you have a positive curvature, you can have cyclic cos. Yes. You mean whether we will have reconstruction after? Yeah, I mean, this depends on the content of the universe. This does not depend, the theory does not tell you that. That's just possible, okay? So if you look at the fraction of potential energy as a function of this phase, this is 0, this is 2 pi, you see that it is basically always between 3 and 4 10 to the minus 6. It could be everything between 0 and 1. It is not everything between 0 and 1. It is highly peaked around 10 to the minus 6. It means that you know what is the potential energy at the bounds in this model. This is a kind of phase space diagram. This is the square root of the potential energy and kinetic energy density. The circle here is the bounds. You are at the Planck density, and the point here is remote past or remote future, okay? Low energy density. So you begin here, you move there, you bounce here, and you go back to the initial point in this phase space. If you want to have points that are here, like that, equispaced at the bounds, you need a very, very specific initial trajectory in the past, which is completely arbitrary. But the other way around, if you take random trajectories in the past with random phases, because of course there is no fundamental reason for the phase of the scalar field to have any particular value, then you end up nearly always at the same point on this circle. It means that the probability distribution function for x is peaked here, and the important point, because otherwise we don't care, the important point is that the number of e-folds of inflation, the duration of inflation if you want, is completely determined by this. And you see that the number of e-folds of inflation is here peaked around 140 and say between 100 and 180 at 99% confidence level. So the interesting point is that not only the model predicts inflation, which is not very hard if you begin at the Planck scale, but it predicts the duration of inflation, which is something very interesting. Yes. Yes, it does depend on the mass, and the mass here is chosen to account for data, because we know the amplitude of the spectrum. Yeah. So, unfortunately, what I've done now is assuming the universe to be isotropic, because we know that in the Friedmann equation the shear term scales as 1/8⁶. And this is why in standard cosmology we don't care about the shear, because it dilutes very fast. But the problem is that the reason why it dilutes very fast is exactly the same as it increases very fast in the contracting branch. So you expect the universe to be highly anisotropic at the bounds. And this is even one of the reasons why people push the ekpyrotic scenario where you evade this anisotropy problem. So you can this is Bianchi 1 as an example with 3 scale factors. I don't bother you with the details. You can write down the Hamiltonian, you can compute the modified Friedmann equation, you can do again the same game, and at the end of the day, what you see is that with anisotropies, your PDF for M is shifted to smaller values. This is with an average shear, now it is around 110, and with the highest possible amount of shear, with a shear triggered bounce, then it is basically smaller than 60 and therefore incompatible with experiments. This is very interesting because it tells you that the real amount of inflation, if this model is correct, should not be much higher than the lower bound set by observations. And this is nice for experiments. This is nice for experiments because for phenomenology of quantum gravity, you don't want to have too much inflation. Just let me make a point for those of you who are pure theorists, completely decoupled from data. The problem of the Planck scale from a cosmological viewpoint is not that it is too small, it is that it is too large. Because in most scenarios of inflation, what was of the Planck size before inflation is today bigger than the Hubble scale. So the problem is that Planckian modes are so big that you can't see them because they are larger than the universe. So the problem of the Planck scale is not that it is small, it's that it is too big, okay, in standard cosmology. So you are happy not to have enough inflation so that your Planck scale modes before inflation might be not too much larger than the universe. Okay, let's take this as a 2-minute break during my talk because I will not take that too seriously. This is just a funny point about de Sitter properties. In the precedent speaker talked about Boltzmann brain. I mean, in de Sitter space, a lot of funny things can happen. If the acceleration of the universe is really due to a cosmological constant, a true cosmological constant, okay, which is very good in the LQG because you can you can really incorporate a cosmological constant in LQG by a deformation of the quantum groups, and it plays the role of an infrared regulator. So I mean, theoretically, this is well defined. And when you go backward in the past, in the contracting branch, at some point the universe will again be dominated by the cosmological constant. Keep in mind, for those who are not cosmologists, that even if lambda is positive, there are two solutions, right? There is the expanding one and the contracting one. So you can have exponential contraction even with a positive lambda. Keep this in mind. So we have exponential contraction in the contracting branch. We are dominated by lambda, and far enough in the future, the universe is basically empty. And then you can fill it with the thermal radiation of the de Sitter temperature, and you can study how it works if the bounce is actually triggered by the thermal emission of the de Sitter horizon. And you can even build like that a cyclic model, because after that, in the future, at one point, the universe will be empty again. And if it is empty, it doesn't mean anything to say that it is expanding or contracting. You know, de Sitter space. In de Sitter space, contraction or expansion is just a matter of choice of coordinates, right? There is no physical meaning for expansion or contraction. And therefore, you can break the symmetry by emitting photons, and depending on the way symmetry is breaking, then the universe is expanding or contracting for real. So this makes a cyclic model that is quite funny. Let's go to serious stuff. Serious stuff for cosmologists is perturbations. How do you compute perturbations in this approach? So I'll make it short, because we are all going to be hungry soon. There are basically two ways to treat perturbations in loop quantum cosmology. One, due to Ashtekar, Aguyo, and Nelson, is really to deal with the quantum fields on a quantum background, building on Lewandowski result, and to build the Hilbert space, which is a tensor product between the background and the perturbations in a mini superspace strategy. So I go to the result, and their result is that the Mukhanov-Sasaki variables that we use in cosmology fill a kind of dressed metric, effective dressed metric, which is neither the real metric nor the one seen by the highly peaked state, which is a kind of mathematical object which allows you to make clear prediction, and this U potential here can be effectively and explicitly calculated through mean values, expectation values of operator. If you do that, you end up with a tensor power spectrum which takes this shape. This is a wave number, and this is a power spectrum for B modes in the CMB. And I want to make a brief point at this stage. You might say, well, that's strange, because small value of k means large scales in the sky, right? So how can this be that quantum gravity makes a deviation at large scale? You would expect quantum gravity to play a role at small scales. And the reason for that is very clear. This is time here, and this is length here. The curves here are physical modes, and the red crosses here is the radius of curvature of the universe. Not the Hubble radius, that's not the same. That's the radius of curvature of the universe. This is a standard Big Bang. If you take a mode and you go backward in time, it will never cross this line, which means that when you go backward in time, the mode will never fill curvature. And this is how we set the background in cosmology. The de Sitter vacuum is exactly defined by this. But in LQC, this is what happens. Now, of course, curvature is bounded from above. So the radius of curvature goes like that. So at the bound, which is here, if you take a mode which is bigger than this mode here now is smaller than is bigger than the radius of curvature. So it fills curvature, and this mode is excited. It cannot be in the Bunch-Davies vacuum. So you see that the modes who fill curvature, they are the big ones, not the small ones. And this is why the quantum gravity effect, which turns out to be the existence of a maximum of bounding from above curvature, density, and so on and so forth, will play a role for big modes, not for small modes, at least in this setting. Okay, and Ashtekar and Aguyo are now refining their models by taking into account the freedoms they have in choosing the initial state. I just want to tell you a few words about the other approach, about how to treat perturbations in this framework. Well, the point here is about gauge fixing. we know that in most physical theories, gauge fixing before quantization can be made with no problems most of the time. But here the constraints we are dealing with are most complicated than Gauss constraints, for example, in Young-Mill theory. And therefore, it might be completely inconsistent to gauge fix a theory before quantization, because then we will not take into account the way the constraints themselves are modified. Otherwise stated, the problem is that a consistent theory must quantize gauge transformations and the dynamics at the same time, and one cannot fix part, the gauge, in order to derive the second, the dynamic, in an unrestricted way, because in GR, dynamics is part of gauge. So we have to be very careful here. And in this approach, called the deformed algebra approach, we are not maybe as quantum as in the previous approach, but we are consistent. We are sure by construction that the vectors of evolution are parallel to the submanifolds of constraints. Okay? So in a nutshell, the idea is the following. We begin with constraints, classical constraints that obey the classical Poisson algebra with structure functions and not constants as in Young-Mill theories. I call k bar and p bar the mean value of the HTK connection and densitized trios. If you want, it's connected with the Hubble parameter and with the scale factor. And the so-called holonomic correction is performed by this replacement, where mu bar is the coordinate size of a loop. This is the standard procedure of loop quantum cosmology. And at the end, of course, you end up with a new structure with new functions here and anomalies that I'm going to tell you about in a few minutes. I want to underline already at this stage that even without anomalies, we would have a new structure of space-time. So the theory is not sterile. It really predicts you something clear about a different algebra of constraints, right? Even without anomalies. But we have to take care about those anomalies by counterterms that do vanish at the classical limits. This is a standard procedure. And the very nice feature is that it is possible to remove all anomalies by using the freedom we have in the way the holonomic corrections are implemented. And the very impressive feature is that the resulting algebra is basically uniquely determined under reasonable assumptions. So not only you can do it, but you can do it in only one way. And what I like very much is that after quite a lot of algebra, I mean the calculations are not very user-friendly, you end up with something very simple. And the resulting algebra is the following, which is nearly the one of JR. The only difference is this omega term here, which is 1 minus 2 rho over rho c. Rho is a density, and rho c is a Planck density. And this omega function, of course, at the classical limit, so rho goes to 0, is equal to 1. So you end up with a standard JR algebra. But when rho equal rho Planck, then omega equal minus 1. And this is very nice, because omega equal minus 1 means that you have an Euclidean spacetime. So that's interesting. You know, 30 years ago, there was a lot of calculation in quantum cosmology by assuming a Wick rotation, because it has a lot of nice properties. It stabilizes your integrals and so on and so forth. But here, you don't put it by hand. It just happens to be that that's not a sudden Wick rotation, that's a smooth evolution of the signature of spacetime. Yes, there are ways to understand it physically, but probably we should discuss later. At the level of the equation of motion, this is what happens. And we have this is consistent. This happens for all types of perturbations. And we have this time here. You recognize the usual Mukhanov-Sasaki equation of cosmology. And we have this additional term here, which changes sign. And you can then compute spectra. This is a tensor spectrum. We have just computed a scalar spectrum, which is basically scale invariant for low k, for the tensor modes that has oscillations, and then an interesting behavior in the ultraviolet. So this is Planck units, and this is the comobile wave number. So you might notice that this is higher than 1, right? And are you bothered by this? Okay. Yeah. Okay. Okay. Of course. So the point you are correct. This is the important point. So this is the co-mobile wave number. If you want to compare with data, you have to change from co-mobile scales to physical scales. So you have to multiply by the scale factor at one time. And the point is that where is the real observational window? What we see actually in the CMB? Is it here? Is it here? Or is it here? This is my next slide, but I can say it now. And the answer to this question depends fundamentally on the number of e-folds of inflation. So if we have a long inflation, what we see is there. If we have and the model is excluded, because we don't see that in real life. If we have a small amount of inflation, what we see is there. And the model is not very interesting because it is the same as JR. And if we have exactly 70 folds of inflation, say, something like the smallest available value, then we are here, and that is interesting. Okay, so these are the predictions of the two different settings of LQC, the deformed algebra here and the dressed metric here. And that's quite interesting because for sub-Planckian modes, you see that although they rely on quite different assumptions, we have a kind of universal prediction. So the theory is becoming to be really understandable. I would like to come back a few seconds to this signature change issue. Between the Euclidean and the Lorentzian phase, there is, as pointed out by Jakub Milcharek, a kind of asymptotic silence surface, which is interesting also because it agrees with the Becquerel conjecture, that is that space points decouple one from the other, the light cone are squeezed. So it might make sense to put initial conditions here. Because up to now I have been very naive. I have propagated modes through the Euclidean phase, but what does that mean to propagate when you have no time? Okay, not a lot. So it might make sense to actually put initial conditions there at the emergence of time. That can be conjecture, as Jakub wrote in the paper, as a kind of symmetry breaking from SO4 to SO13, as we can see, for example, in nanomaterials when the nanowires do a line, and the time would be the analogous of that here. The point is that at the surface, the space points are physically disconnected. So it makes sense to assume, for example, a white noise spectrum, and you can propagate in time, because white noise because there is decorrelation, at least up to some scale, which is of the order of the Planck scale, and you can propagate the spectrum in time and try really to investigate what it gives at the phenomenological level. The very interesting progress that was made recently by Martin Boywald and Jakub Milcharek is that in the mathematical literature, the trichotomy problem has been studied quite long ago. So this is basically the kind of equation we have, and depending on the sign of y, this is either elliptic or hyperbolic. And when studying how to put initial conditions for those equations, if we want to keep predictive power, of course, it has to be done in a kind of hybrid way, depending on whether you are in the Euclidean or Lorentzian part of the space-time. So there is a very nice balance, because what they have shown in this approach is that, on the one hand, a new function has to be set for each mode at the bound, not at the bounds, but at the emergence of time. So there is something new, which does not come from the past, but the normal derivative of the field keeps memory of what happens before the Big Bang. So there is a very interesting situation, which is you have something new, but you have something deterministic too. Okay, so this is something that has to be studied. And finally, I like very much now what is called hybrid quantization, which is being developed in LQC, which tries to put everything together, not to neglect back reaction, and the first results, especially in Gaudi models, are very promising. I don't have time. Okay, this is a second 2-minute break. Second thing that I would not take too seriously. It's interesting to make some links between LQC and the multiverse. Of course, in a de Sitter background, if you consider the nucleation of an anti-de Sitter bubble, in the standard view, it will reach a singularity, of course, infinite amount of time. But here, you don't have any more singularities. So it was tantalizing for Vilenkin and Garriga to assume that those anti-de Sitter bubbles will bounce, thanks to the loop quantum cosmology mechanism, mechanism, and at the bounce, what happens? Well, of course, it depends on the potential you assume for your field, but they have been able to calculate the mean displacement of the field at the bounce, and therefore to have a kind of average picture of the multiverse to define the measure, and that's not very serious, I think, but that's very funny. Okay, last part of my talk, very brief one because we are hungry. So this is just to add a new proposal to the list of possible way to account for black hole informations. So if you have never heard about it, I don't have time, but I strongly encourage you to look at it. Ravelli, Vidotto, and Hagar have suggested something like, I don't know, 2 years ago, an interesting model, which is now quite a lot studied, that black holes are not actually black holes, but are bouncing objects. I'm telling you a few words about that to connect with the previous talk, and because this is not really loop quantum cosmology, but this is the application of the ideas of loop quantum cosmology to something else, which is a black hole. After all, if the universe bounces, probably black holes are bouncing too. It's true that the singularities are not exactly the same, but that they are not that different. So what they have shown, and I will not explain at all right now, is that it makes sense. That it's possible, of course not that we don't know that's true, but it makes sense to glue a classical contracting black hole solution to a classical expanding white hole solution with a quantum region in between, and with quantum effects, quantum gravity effects that are big enough so that you evade to some extent the Norea theorem, and you can really do that. Of course, you don't have anymore an event horizon, you have a trapping horizon. Of course, it immediately solves the information paradox because all what goes in goes out. And in this view, what is somehow interesting, I think, is that the Hawking evaporation is not anymore very important. It's just a kind of dissipative perturbation to the system. You know, if I throw a tennis ball from here, it goes to the ground, it bounces, and it does not bounce exactly at the same height. It will bounce here, for example, because there is heat dissipation at the bounce. So in this model, black hole bounce, and the Hawking evaporation plays the role of heat dissipation. You lose a little something by Hawking evaporation, but most of what goes in goes away. So what I like about that is that it might be, well, that's not easy, but it might be testable through small black holes, of course, because the bouncing time has to be small enough to be seen. So why don't we see white holes in real life? Of course, the reason is just time dilatation, of course. The bounce takes a fraction of a second in proper time, but seen from the exterior, because of the time dilatation, it takes much more than the edge of the universe. So this is the obvious reason why we don't see white holes, except if we focus on small black holes, on primordial black holes. We don't know if they exist, but we can hope they do exist. Actually, I have been very fast, so I will not use all the time I am given. And when you do that, so we went through a complete simulation of the process with many approximations because we don't yet know the details. But the interesting point is that you might expect an emission around 100 MeV, which is an extremely low energy compared to the Planck scale where things happen to take place. And the reason for that is that what matters is density, is not size. Okay? So when your black hole collapses, you reach a core of the Planck density, which is not at all of the Planck size. Of course. I mean, if you take the current universe, you contract it. When it reaches the Planck density, it does not have at all the Planck size. It is larger than the Planck size by many, many, many orders of magnitudes. And for this reason, together with quite a lot of other considerations, you end up with a gamma ray signal in this region, which might be with a lot of cautious, compatible with some of the very short gamma ray bursts that are actually measured and not yet understood. In a better, refined version of the model, it was understood that the previous case was only a particular case, so now we have a clear picture of what is happening here, and the bouncing time is unfortunately a kind of free parameter, so it really depends on something that the theory cannot tells you what is its numerical value. So we have evaluated the maximum distance in the universe at which we might observe this phenomenon depending on this 3-parameter case that can vary on a very wide range of orders of magnitudes, and depending on the value of this parameter you can either see it from up to the Hubble scale or up to the galactic scale. The point is that the bouncing time is proportional to m squared. So this is why it is generically faster than the Hawking time, which is proportional to m cubed. Unless, of course, you put here a huge constant and a small mass, and it can even become larger. And this is my final plot. What I recently did was to calculate the integrated emission from a possible distribution of bouncing black holes. This is what it gives. So I cannot tell you what is the energy here, because there is a free parameter of the model which will allow you to rescale the energy. So I don't know at which energy we should look, but I can tell you what is the shape. And the shape is this interestingly distorted Planck law. So there is a kind of black body spectrum with, for a reason we understand very well, this little something here, which, as far as I know, is not exhibited by any other astrophysical phenomenon. So this is one possible hope for future detection. So my conclusion is that, to be honest, there is no, at this stage, smoking gun prediction from all approaches to LQC. I am unable to tell you this is a clear point that LQC tells you about the universe, except that there is a big bounce instead of a big bounce. This we cannot see directly. However, there has been many progress in the recent years, and what is interesting is that we are now making links with observations, and some very specific settings of very specific approaches to LQC can already be excluded. So for me, this is a sign that the field is alive. Thank you.
The mic for no, because actually it's recorded.
Okay. So about this bouncing black holes, I think on one slide you had something about radio burst. Do you mean this fast radio burst, the 12 events that people have seen? Or?
Yes. So yes, it's written here. You're correct. So Carlo Rovelli was very excited about that. I am a bit less than he is.
Okay. What's the reason? Or for excitement or not excitement?
Yeah, it's tantalizing. You have observations, you don't know where they come from, and you have a theory which is compatible with those observations. So of course it is tantalizing. Still, it's very unlikely, because first you need a theory to be correct, of course, and then you need a quite high amount of primordial black holes that are somehow tuned to have exactly the required mass for the theory to explain the data with an amount, with an average density in the universe which nearly saturates the dark matter bound. So strictly speaking, this is not impossible, but in my mind, it's pushing it a bit too far. You see, I wouldn't say that this is an obvious explanation. I'm sure astrophysicists will find easiest explanations. That's my guess.
Okay, so other question?
Why the transition time is so small? Because from gravitational instantaneous estimation, usually in dilute gas approximation, one could expect that this is exponentially suppressed with the black hole entropy. In other words, from a tunneling from a very macroscopic configuration to another macroscopic ones, I expected a very large suppression. So why not happens in this case? Why is so small the time? Is smaller than Hawking complete evaporation.
Yes, but Hawking time is huge for most black holes. For astrophysical black holes, Hawking time is huge, right?
This is the question.
We have to go through the calculations.
It's an assumption.
I have no intuitive explanations for that.
Okay, it's an assumption.
No, I mean, it's hybrid. What is assumed is that it is tuned so as to solve the information paradox. So this is the part of the model which is ad hoc. The part of the model which is not ad hoc is that you have very strong constraints, because, of course, if the quantum effects are confined within the horizon, this is impossible, because we have no air theorem. Once the event horizon is formed, it is formed. And classically, you cannot go away, of course. So you have to assume that you still have quantum effects outside the horizon, otherwise it just cannot work. And the idea beyond that is that, of course, at every instant of time, quantum effects are extremely small, but when they are integrated away during a huge amount of time, then they can become big, exactly like if you take a uranium a nucleus. Of course, if you wait for 1 second, the quantum effects are completely negligible. But if you wait 6 billion years, it has disappeared, for sure. So the quantum effect at every instant of time is very small, but integrated over the edge of the universe, of course, all the uranium, I mean, some kind of unstable uranium nuclei have decayed. They just have decayed. So this is basically the same setting. I can show you the details. I have no clear, intuitive answer.
Okay. Any other question? If not, let's thank the speaker again.